Projectile motion type 2. Projectile motion type 2 is when an object is launched upwards at an angle, then lands at the same height it was launched from. For example, kicking a soccer ball across the field. The analysis is similar to projectile motion type 1, except the initial velocity now has a vertical component as well as a horizontal component. These problems typically start as a ball is thrown at 10 meters per second at an angle of 20 degrees above the horizontal. How far away will it land? How high will it go? In that case, the given speed, v0, which is here's 10, is the magnitude of the velocity vector. It is the hypotenuse of a right triangle. We need to solve for the sides, the components of this velocity, v sub x and v sub y. Let's go ahead and solve that problem. A ball is thrown at 10 meters per second at an angle of 20 degrees above the horizontal. How far away will it land and how high will it go? First, resolve the initial velocity into its x and y components using trigonometry. Don't forget SOHCAHTOA. First, let's start with sine theta. So sine is opposite over hypotenuse. So here's our angle. Opposite is going to be v sub y, right there, over hypotenuse, which is initial velocity. Therefore, if we solve for v sub y initial, we get the hypotenuse times sine theta. Therefore, we plug in the hypotenuse, the length of this vector is 10. We multiply it by sine 20, and we get 3.4 meters per second. So that is our vertical component of initial velocity. Then, it's only a 20-degree angle, which is a pretty low angle. So a lot of this velocity is going to be in the x dimension. The x component is related to the cosine of this angle since this is the adjacent side. Cosine theta is adjacent over hypotenuse. Therefore, adjacent is Vx, the hypotenuse is V0. Solve for Vx initial, and we get V0, the hypotenuse, times cosine theta. So we take that 10, multiply it by cosine 20, and we get 9.4 meters per second. Yes, this is a very low angle, so most of this velocity is in the x dimension. So it's good that we got a number here that was larger than that number. Compile the list of givens and calculated x and y velocity components. Alright, so if we're assuming that the ball goes something like that, we're going to say that this is 0 meters, this is x over here, and we're trying to calculate how far that is. And in the y dimension, we're starting at a height of 0, and then it lands at a height of 0. So that gives us these four quantities here. We already calculated the x component of initial velocity to be 9.4, which doesn't change throughout the entire flight, since there's no acceleration in the x dimension. There are no forces pulling the ball to the left or right, so there will not be a change in speed. It will be constant in the x dimension. However, in the y dimension, it starts out with an initial velocity of 3.4. It will get smaller and smaller till it reaches the top, where the y component of the velocity will be 0. Then it will speed back up as it falls. So it will be changing throughout the flight. This is due to this force of gravity providing an acceleration of negative 9.8 meters per second squared. Do we currently have enough information to calculate how long the ball will be in the air? Yes. Just like with type 1 projectile motion, we currently have enough information to solve for air time. Use kinematics equation 2 in the y dimension. However, unlike type 1, the middle term is no longer 0. Substitute in the givens and solve for t. Alright, so we're starting with the second kinematics equation in the y dimension. Usually I would say solve for t first and then plug in givens, but in this case it's actually easier to just eliminate a bunch of terms and plug in things first. So both y initial and y final are both 0. Therefore we can move one of these terms over to the left side. Negative v0 t equals 1/2 a t squared. Divide both sides by t. This one goes away completely. This one, we are left with just 1t. Finally, solve this for t, so multiply both sides by 2, divide both sides by a, plug in our numbers, the negative signs cancel, and we get 0.7 seconds of airtime. Add time to the list of givens. Look, it's here on both sides. Next, we can solve for how far away it will land, x. Now that we have time, we can use kinematics equation 2 in the x direction to solve for x. So our initial position is 0, there's no acceleration in the x dimension, therefore how far we go is how fast we're moving for how long. Distance equals speed times time. We're traveling at 9.4 meters per second for 0.7 seconds, which means we have traveled 6.6 meters horizontally. Do we have enough information to solve for the maximum height that the ball will reach? Yes, but a new observation is required. At the very top, the ball stops traveling upwards. It stops moving in the y direction, then begins falling back downwards towards Earth. In that instant, there's no velocity in the y direction. However, it still has velocity in the x dimension. At the peak of the projectile's trajectory, all of the velocity is in the x dimension. Therefore, the velocity at the top in the y dimension equals 0, and velocity at the top in the x dimension equals whatever velocity it already had. Another observation, in projectile motion type 2, the time to the top is equal to 1/2 the total air time. It takes 0.7 seconds to reach the ground again. Therefore, it takes 0.35 seconds to reach the very top. Use kinematics equation 2 in the y direction to solve for the maximum height, y at the top. So here, we know that we're starting from the ground, and we have an initial velocity in the y, we have an acceleration in the y. We're going to plug in our values into this equation. Don't forget this negative sign, and remember to only substitute in the y component of the initial velocity, not the 10 meters per second, right? We want the 3.4 meters per second. And we see that the ball reaches a vertical maximum height of 0.6 meters. There are equations for airtime, horizontal range, and maximum height, but they're not worth memorizing. They can be derived algebraically by combining kinematics equations. Let's calculate time in the air using the y direction equations. So instead of having an actual value, let's just solve for the y component of the initial velocity, vy naught, right, initial velocity. So we know that the y component of the initial velocity is the length of the hypotenuse times sine theta. So we're just going to use that in here. Since this is type 2 projectile motion, we know that y is going to be equal to y naught. So they're both going to go away. Then we can move one of these, like let's move this over to the other side. We know the acceleration is negative g since this object is free fall. And we can solve for t, right? Divide both sides by t. We're left with 1t here. Multiply this side by 2 over g, and we get this equation for air time. Now this equation will only work for projectile motion type 2, so you should learn how to derive it. For maximum height, you're going to use the second kinematics equation in the y dimension. Now remember, the initial velocity in the y dimension is all of this, v naught times sine theta. We know the acceleration is g, we put that negative sign right here. We know that the time to the very top is the total time divided by 2. And so here, we're actually going to plug in what we solved for here for air time into that equation for t there and there. So you can see there's a lot of algebra here. But at the end, yes, there is an equation for maximum height. And it's only dependent on the initial velocity squared, the angle, sine of the angle squared, over 2g. Finally, horizontal range. How far you go is how fast you're going and for how long. Remember, in the horizontal dimension, it's constant speed. So this is the initial x component of the velocity. We're going to plug in that time, air time, into that equation, and that will give us an equation for how far a type 2 projectile will go.